Hey, I'm Nathan Mikulski. Welcome back to our machine design lectures. This time we'll be talking about topic 5, which is fasteners. Let's jump into it. So, when you think fasteners, you think of screws, bolts, nuts, rivets, nails, that kind of stuff. In this case, we're going to be focusing on nuts, bolts, and washers, okay? What are the main functions of fasteners? Well, in this sense, we're going to be talking about the main function being to hold things together via non-permanent joints. Non-permanent meaning you can take them apart, put them back together, and stuff like that. Why do we use that? Because of field disassembly or assembly, or you need to take something apart by yourself, for maintenance, or for adjustment of the pieces. Now, what are some of the design considerations we have to have with fasteners? Well, we have to have, for jointed structures, effective stiffness of both the fastener and the materials, and strength and fatigue loading of the fasteners and materials. Let's jump into it. So for the effective stiffness, let's look at the fastener stiffness first. There's a lot of different factors that will come into it, but here are some of the main considerations. The length of the unthreaded grip, the length of the unthreaded in the grip, the length of threaded portion in the grip, the area of the unthreaded portion of the grip, the area of the threaded portion of the grip, the effective stiffness, which is our main goal, the length of the fastener, and the threaded length of the fastener, all given by LD for unthreaded in the grip, LT for threaded portion in the grip, AD for area of unthreaded portion, AT for area of the threaded portion, which can be found from tables. All these other ones can be found from equations. And capital KB for fastener stiffness, L for length of the fastener, and LT for the fastener length of the threaded portion. Now you might be thinking, why are we going to use KB for the stiffness? Well, it's kind of similar to the springs, as we see here. So if we're going to have, say, a rod, which we'll use as a representation of our fastener, if we apply a force, and it has material properties of E, A, and L, our X, or if you remember from, say, mechanics of materials class, is FL over EA, which is deformation stuff. And we have F equals Kx, which is an equation for the spring constants, which is being a spring constant times the length that it is compressed or extended. Now, if we rearrange and combine those two equations, we can get K equals EA over L. Now, if we think about these being springs, we can think about them as combining springs into making one singular spring that could have the representation of, say, this stuff with the material properties. So if we look at this, say we have a bolt here with our unthreaded portion and our threaded portion being two separate spring constants because of all the varying geometries and stuff like that. So we'll have K1 for this unthreaded portion, K2 for the threaded portion, still with our F supplied. We can use this equation to achieve a singular equivalent spring constant with 1 over K being the total one, equaling 1 over K1 plus 1 over K2, or K is equaling K1, K2 over K1 plus K2. Now, how does that really work out for us? Well, we need to know our effective stiffness in order to apply our stuff properly. Let's take a look at this example, okay? This example is 8.2 from our lecture slides, but I think it's a great representation of what we need to do. Firstly, we have this scenario here. It's a bolt with 2 washers and 2 pieces of material that's holding together. Each of the washers is 0.083 inches in thickness, and each of the materials is 1 inch in thickness. And our washer down here has a thickness of 21 over 64 inches. So, and material properties of E equaling 30 mega-psi, ultimate strength being 47 kpsi, and the yield strength being 25 kpsi. And this is given to us as kind of our bolt instruments, measurements, stuff we need to go off of. 3/8, this 3/8 designation here in the front being the width of the bolt. 16 UNC is just other material classifications, and grade 8 being the grade of the bolt, meaning the higher the grade, the stronger the bolt is for this, in this case. So if we apply these equations that I will go through with you again, but if we have to find our unthreaded length, threaded length, the areas of the two, and like the overall length in order to find our stiffness of the material. So let's jump into it. Our length, this L, which is the length from fastener or end of the washer to end of the washer, is 2 times our 2 washer lengths plus 2 inches, being the thicknesses of these. And we get 2.166 inches. Now our overall length, which is going to be taken from the head of the bolt to the end of the washer, or to the end of the connecting nut, is going to be is essentially the L plus the thickness of the washer, which is again 2 times 0.083 plus 2 plus the 21/64 being the thickness of the washer. And we get 2.5 inches. Now our LT, or the length of the threaded portion, which should be somewhere in here, is going to be 2 times the diameter of the bolt plus 1/4. And we were given the diameter is 3/8 inches. And, sorry, that's not the diameter of the bolt head. We were given 2 times 3/8 inches as the diameter of the bolt, plus the 1/4 inch equals 1 inch. This is just an equation we were pulling from our slides. Now our LD is going to equal this L, the overall length, minus the LT, which is the length of the threaded portion. And this is going to give us the length of the unthreaded portion that is in the compression, which is our 2.5 minus 1, so we get 1.5 inches. Our threaded portion that's in the contact would be the overall length that's in the contact minus the unthreaded portion that is in there. So 2.166 inches minus 1.5 inches gives us 0.667 inches. Now our area of, so our unthreaded area is going to be pi over 4 d squared, which is our normal area of a circle, which will give us 0.1104 inches squared. Now our AT, which we were pulling from tables 8.1 or 8.2, is going to be 0.0775 inches. Why is this case? Well, because if you know, as your screw, you have ups and downs as the threads and then unthreaded portions, and it's just it's hard to get the area. So this is kind of taking the average of those and putting it into table format, which we pulled from based off of our other material or our other bolt classifications. Now, let's put it all together into our KD equation, or our effective stiffness equation for our bolts, which is AD times AT over E, or times E, over AD times LT plus AT times LD. Now plugging in all of our values from here and our E from up here, we get a value of 1.35 micropounds per inch, which is good. Now, let's move on to our member stiffness, which we'll use to demonstrate over here. To find our member stiffness, we have to look at something called a frustum, or frustrum. A frustum is essentially a segmented cone. So basically you take off the top pointy part of the cone and you're left with this. Now with the hole in the middle for like the bolt, it looks like it's a 3D cone, but here represented in 2D, it's gonna look like a parallelogram or rhombus that has our hole in the middle, and if you segment it into 3D, it's basically a cone without the top and a cylinder missing in the middle. And we're going to use that to evaluate our stiffness in our members. Now, here we have our equations for the member stiffness based off of these properties of our frustum. Deriving it, and we're going to get to use our useful equation, which is going to be 0.5574 pi times E times D, a little d, which is our little d here, over the natural log of 1.55 t plus big D plus little, or minus little d times d plus d, over the same thing but changing plus and minus symbols here. Now we're getting all of those from here. This is assuming we have standard washer face diameters of 1.5 times d little d, and an angle of alpha equaling 30 degrees. If not, we have to come back up here and do our not so fun equation, but it is still possible to figure it out. Now let's apply it to this previous example over here. In this case, since we have multiple things, we're going to have multiple frustra or frustrums. And we are able to add them up in a similar way of adding up springs in series, which would be 1 over k, or 1 over the total k is 1 over k1 plus k2, that kind of stuff. So let's draw it out. So we're taking this and putting it over here. And since we have washers are technically going to be part of our members, we need to include them into this. So we're going to draw our lines here, and at our middle point, where the two bases of the biggest frustra are going to be equal. This case happens to be in the middle because of symmetry, but that's not always the case, and it divides out into 4 different frustra. Now, we have our littler frustra up top from the washer, given like this. Our D1 is going to be based off this part of the bolt, and our little d is the thickness of the bolt going through there. And we have our thickness of the frustra given by the thickness of the washer. Now, we can apply this equation, because they're going to be touching like it's shown here, and we can see that our second big D is going to be equal to the D1 plus this little extra part given by this, represented by this 2 times T times tangent alpha, stuff like that, which is kind of represented over here. That's this little extra part hanging off of the D. And this is kind of just the math proving it. And we can use these plus the D equation plus the T's to plug into here and find the 2 frustra for find the 2 stiffnesses for each of the frustra. And then in this case, we're multiplying each one by 2 because it's symmetric, and that'll give us the total stiffness of the member. Now, let's move on to mechanical stability. For mechanical stability, you have 2 different types. You have static or you have dynamic. For the static case, you have a lot of different stuff coming into play. So you have deformation equaling the force over the stiffness, or it essentially derives from this equation of F equals kx. It's similar in nature to that. And notifying that the deformation in the bolt and the member is going to be the same, you can set them equal to each other and solve to find the force or the constant for each. Now, you'll also need to know what the stiffness constant is. Stiffness constant is simply the fastener stiffness or bolt stiffness over the bolt stiffness plus the member stiffness, which we can find from our initial topic over here. Now, we also need to know about resultant bolt loading. So our FB is going to be equal to our PB plus FI, which equals our C times which is our stiffness constant times force P plus Fi. And on members, something similar, Fm equals Pm minus Fi, which equals 1 minus C times P minus Fi. These are just simple applications, and we will be given stuff that we can rearrange to solve for all of these. Say we have more than 1 bolt, we can simply divide our P divided by the number of bolts, and that'll give us the force per bolt. Now we need to work on factors of safety, because that's always important. You always want to be safe, and you always want to have a factor of safety that will not cause failure and be plenty safe for everybody. So our factor of safety is going to be based off of our SP over our sigma B, which is going to be equal to our SP times AT over our AT, remember, is our AT from up here, times our C, which is our stiffness constant, CP minus Fi, which is all be given to us. And our load factor is another thing we need to talk about, because it could be different depending on how it's loaded and stuff like that. And it's essentially a rearranging of this. And our SP times AT minus Fi over CP. And our joint separation factor, which is represented by NO, is going to be our Fi divided by P times 1 minus C. That's all for static loading. These are all different variations of stuff that will be very important for usefulness. And lastly, let's go over our dynamic. Dynamic is similar to static, but of course it's also not, because it's moving. And we need to have our factor of safety rearranged to counteract or to account for the dynamics, which will be our NP, which equals to our SP over theta B, or sorry, sigma B, which equals SP AT divided by CP plus Fi. Remember, all those should be given in, say, problems or scenarios. in real world problems, you're going to know the stuff, you're going to know those properties so you can rearrange and solve to find or use the factors of safety to be helpful. Thank you. This should be all about our factor of safety. We'll see you next time.